after he starts to play with this ratio. Okay, so entropy is going to increase if the heat is entering the system. All right, and entropy is going to be negative if the heat is exiting the system. All right, so if positive, so which means that if the region is heating up, the entropy is going to go up. If the region is cooling down, the entropy is going to go down. That's what it means. Okay. All right, so entropy is positive when the region is heating up. All right, so the region which is going to be heating up is the region which is at a cooler temperature. All right, so you get that. So C means cool or cold. So the cooler or colder region is going to heat up, which means that the entropy of that region is going to go up. And the hotter region is going to end up losing heat, so which means that the hotter region is going to cool down, so the entropy of the hotter region is going to go down. Okay, so we're able to express the concept of entropy. Oh, you know, if the system is heating up, its entropy is going to go up. If the system is cooling down, its entropy is going to cool down. All right, so the hotter region is going to cool down. This is what this means, and it's losing heat, obviously. And the cooler region is heating up. Its entropy is going to go up because heat goes from hot to cold, obviously. So the cooler region is going to heat up. The hotter region is going to cool down. Entropy of the cooler region is going to go up because this region is heating up. The entropy of the hotter region is going to go down. All right, so this is what happens on online education. I repeat myself like a million times. Normally, I would look deep into your eyes and make sure that this stuff is tattooed to your soul in one single statement. All right, because I can't see you guys. I have to keep repeating myself like a trillion times. So the conclusion number one, the irreversible processes increase the total entropy of the universe. So the question is, what the hell? How did we come up with that? How did we come up with that conclusion like that? Okay, I made that statement before, like, I don't know, about an hour ago. I said you will hear that at least 50 times by the time I'm done with you guys. We're probably repeating it the 10th time already. So the question is, how do we know that? How does that irreversible process increase the total entropy of the universe? I gave you an example of doing the lawn, but mathematically it's still going to work out the same way. All right, so if it's an irreversible process, the irreversible processes will increase the total entropy of the universe. If it's a reversible process, though, the total entropy of the universe does not change. Okay, so this is the amount of heat that goes into the system at this temperature. All right, and if it's a reversible process, you get back to the same point. So once again, the heat at that temperature is going to be the same. So which means that during the reversible processes, there's no change in entropy. Okay, real life does not have any reversible processes, so which means that total entropy of the universe is always going to go up. All right, so that requires a justification. All right, so when the entropy of the universe increases, and it's going to keep increasing every time there's heat transfer from hot to cold, the amount of energy available to the useful work is going to diminish. So what does it mean? Look, the amount of energy available to the useful work is going to diminish. All right, so here's the efficiency formula. This is the amount of work that you could do per amount of heat that goes into the system. So according to this, the amount of energy available to the useful work is going to diminish. So just solve for W, that's the amount of work. This work is going to be done at this efficiency, which means that this efficiency is just the percent. It's going to tell you the percentage of heat which is going to get converted into useful work. That's what it means. Now we got an expression for efficiency. Efficiency is expressed in terms of the ratio of the temperature of the cooler region to the temperature of the hotter region. Boom, boom, boom. All right, we'll do a back substitution. So now let's think about what the statement means. Look, every time there's heat transfer, every time there's a transfer of heat, the heat is going to flow from hot to cold until there's no temperature difference. Okay, my hot coffee is going to be at room temperature or something. Okay, so when my coffee is at room temperature, there's not going to be any heat flow. So when these temperatures are the same, what happens to this ratio? It's going to be 1. So what is 1 minus 1? I don't know. It's a lot of work, but I know the calculus is required, so you should be able to do this. I'm guessing it's going to be 0. So when the temperature difference is 0, that's the 0 law of thermodynamics, by the way. Efficiency is 0 at that point, so no work is being done. Okay, so let's get back to this statement one more time. Ignore the math. Okay, look, entropy of the universe is going to go up every time there's temperature difference, right? Every time there's heat flow. And the heat is going to flow until there's no temperature difference. Okay, as long as there's temperature difference, you can do useful work with the heat that flows from hot to cold. But eventually, hotter region and the cooler region is going to tend towards an equilibrium temperature. So once they reach an equilibrium temperature, there's not going to be any heat flow. If there's no heat flow, you cannot do any work using a heat engine. That's what it means. All right, so that's the story. Okay, and this is otherwise known as the heat death of the universe. So what that means is the universe is cooling down. It's going to keep on cooling down until there's no temperature difference. Once there's no temperature difference in the universe is going to be 100% dead. That's what it means. So you cannot extract any useful work out of that universe. Despite the fact that we've been talking about heat engines as if they are cars, this and that. Again, this one, you guys, you are a heat engine, so am I, and so is every living thing in the universe is a heat engine. All right, whatever it is that you're eating, all right, turns into calories at the end. All right. This heat transfer of heat is what drives the universe. The universe itself is a heat engine. And which means that if there's temperature difference, there's heat flow. The universe is at 3 Kelvin. We are here on Earth, it's 310 Kelvin. That's what your body temperature is. As long as there's temperature difference, there's heat flow, there's life in the universe. As soon as everything is at an equilibrium temperature, that's going to be the end of us. The zeroth line is going to kill us all at the end. Okay, so that's what it means. That's the ultimate fate of the universe. All right, so the conclusion number 4 is the entropy goes up, which means that the disorder of the universe is going to go up. If the entropy is going down, that means that the disorder is going to go down. And we know that every time there's heat flow, the entropy of the universe goes up. So also we know that the time flows from our experience of time in the forward direction from past towards the future. So we say that the time points, at least our experience of time, arrow of time, points in the direction of the increased entropy of the universe. All right, so increased entropy of the universe does not cause the time to flow in the forward direction. That's just a myth. It's just the arrow of time, meaning that our experience of time always points in the direction of the increase of the disorder of the universe. That's it. All right, there's nothing to read into it.
Because the Carnot cycle could run just as well in reverse. It was the picture of the ideal engine, the most efficient machine the laws of nature could possibly permit. But with Carnot's early death, his ideas, practically ignored from the beginning, seemed destined for oblivion. And that's probably where they would have ended, had not 2 great scientists taken an interest in Carnot's theory. Rudolf Clausius, a German physicist, and William Thomson, the Glasgow professor of natural philosophy, who would become Lord Kelvin, rescued Carnot's original writings, and from these very pages brought forth the science of thermodynamics. Within Carnot's reasoning, Clausius and Thomson saw an amazing fact, and they saw it in terms of an astonishing mathematical simplicity. In Carnot's ideal engine, the ratio of the heat taken in to the heat wasted was the same as the ratio of the 2 absolute temperatures needed to drive the engine. In other words, and this was the ideal that stemmed from Carnot's imagination, something that goes in is the same when it comes out. If it's not the heat, and if it's not the temperature, what is it? It's the heat divided by the temperature at which it flows. And according to Clausius, that's entropy. In a Carnot engine, some entropy flows in at high temperature, does its job, and the same amount of entropy flows out at low temperature. So an ideal engine not only conserves energy, it conserves entropy as well. That's the ideal. But what about the reality? In the real world, with a clanking, hissing, whistling, puffing engine, what really happens? For one thing, all engines conserve energy. The work equals the difference between the heat in and the heat left over. But using the same temperatures, a real engine does much less work than Carnot's ideal. It does less work and leaves more heat to release. So even though the entropy that flows in might be the same as Carnot's, the entropy that flows out is bigger. That's an amazing fact. The entropy that flows out of a real engine is bigger than the entropy that flows in. Could this mean that real engines create entropy out of nothing? As a matter of fact, yes. That's because in real engines, heat flow isn't isothermal. Power strokes aren't adiabatic, and there's always friction between moving parts.
Okay, so problem number 6. Okay, so there's going to be heat flow from hot to cold. Okay, so we'll take a look at the change in entropy for this one. Okay, so take a look at the temperature, take a look at the temperature. So the hot region is 650, the cooler region is going to be 350. So this is 650. All right, so there's going to be a temperature drop from 650 to 350 here. In this case, the temperature difference is going to be 650 to 150, so there's a huge temperature difference between these two regions that we're looking at. Okay, and do a comparison. Okay, so we'll let the region cool down to 350. Then we'll let the heat flow from here, from this temperature to a lower temperature. And then what we will do is we will compare the work done, or the work that we're going to be able to extract from that system. Okay, there's a mathematical way of doing it, but I think I'm more interested in a conceptual understanding of it. Okay, so every time there's heat flow from hot to cold, the amount of heat available to do useful work diminishes. Okay, so that's one of the conclusions of the entropy principle. All right, so every time the heat flows from hot to cold, all right, so the entropy of the universe is going to go up. Every time the entropy of the universe goes up, the amount of heat available is going to diminish. This problem is designed to illustrate that. Okay, so if there's a heat flow from this temperature, which is 650 Kelvin to 150 Kelvin, this is the amount of work that you're able to get out of it, right? But if you let the region cool down to 350, notice that there is a reduction of 300 Kelvin here. The amount of heat available to do useful work also diminishes. So look at the amount of work that you're able to get out of it versus the system. And this happened because you let the region cool down. Okay, so that's it. I mean, conceptually, you can see that happening. All right, let's check to see how fast we could do this, because it's going to take us through the same argument. And I'm just trying to decide whether or not I want to do that. I feel like I have to do it because there will be multiple choice questions, multiple choice math questions. Okay, so let's just, now that we know how it goes conceptually, let's just do this real fast. Hot region is at this temperature, the cooler region is going to be at that temperature, so that's what we got. Okay, and then what I'm doing is I'm going to take the hotter region, let it cool down, and then I'm going to place the heat engine between 350 and 150. So when I don't let the region cool down, I'm going to take a look at the amount of work that we can extract from the system and compare it to the amount of work that we will extract from the same system when you let it cool down. All right, so Kelvin temperatures are being expressed in terms of Fahrenheit. The cooler region is actually really, really cool. Evidently, it's negative 198 Fahrenheit. All right, so initial temperature is 710, and then it's end up creating a huge temperature difference. So there's going to be a lot of heat. So this is the amount of heat actually is going to be flowing into the region from the hotter source, in essence. All right, so let's take a look at the amount of work being done, if that's the case. So the efficiency of the engine is going to depend on the ratio of the temperature of the cooler region to the hotter region. And we got the temperatures of the cooler and the hotter regions. Just don't forget, guys, on the multiple choice section of the test, always use the Kelvin temperatures. All right, don't use Fahrenheit or Celsius, just use Kelvin. All right, so that's the formula that we will get to use. All right, so the work done when this region is not allowed to cool down is going to be this. When that region is allowed to cool down to 350 Kelvin, this is the amount of work that you're able to do. All right, so which means that every time there's heat transfer, and the heat is going to be transferred out of the region because it's cooling down, the amount of heat available to do useful work goes down. All right, so this is a book way of explaining something which is fairly straightforward. You didn't have to do mathematics for this one, but it gives us a chance to use a little bit of math. All right, so side note is one of the conclusions that we've seen before. So during the irreversible process, the entropy of the universe is going to increase. So which means that the energy, when we talk about energy, we're talking about heat available to do useful work is going to decrease. All right, so when these two temperatures start to come very close to each other, this ratio is going to start to get bigger and bigger and bigger. As a result, the efficiency of the system is going to start to become very small. Okay, so the reversible process is not going to change the total entropy of the universe, obviously.
Whether it's trade winds of the great oceans or the diesel engines of the great ships that ply them, all engines work because heat in motion can set matter into motion. For several hundred years, the heat engine has gone far and wide, But past or present, the heat itself goes only one way, from high to low temperature. The existence of any engine on Earth, including the Earth itself, depends on one of its parts working at a higher temperature than another. In nature's engine, for example, powerful currents are driven through the Earth's atmosphere by the difference between the equator's temperature and the temperature at the poles. From pole to pole and engine to engine, the principle is the same. In this vehicle, it's the difference between the temperature of the exploding gasoline and air in its cylinders and the circulating water of its cooling system. Steam engines operate between the high temperature of the firebox and the low temperature of the atmosphere. The bigger the difference in temperature, the hotter in one part of the machine, the cooler in another, the better the engine works. But if the fuel stops flowing and the hotter part of the engine is allowed to cool down, the engine grinds to a halt. And obviously, that can spell trouble. If every part of the engine has the same temperature, if all motion ceases and there's no vitality left, the engine reaches its final state, the state of equilibrium. From a scientific perspective, then, what's the picture?
In this molecular dynamics calculation, each pair of atoms is programmed to interact with a realistic interatomic force.
So then what really happens when a warm body is brought into contact with a cold one? Thermal energy spreads from warm to cold until both bodies reach the same temperature. This is the state of thermal equilibrium. At first glance, thermal equilibrium seems different from the mechanical idea of stable equilibrium, which keeps a body safe from falling. But take a closer look. When a falling body hits the ground, each bounce is smaller than the last. Why? Because the kinetic energy of the body as a whole becomes transformed into the chaotic motions of the atoms that compose it. And that process is very similar to heat flowing into a cold body, and the end result is the same. All of the available energy eventually becomes shared out as kinetic and potential energy of random motions of all the atoms. Therefore, although the idea of equilibrium seems the ultimate in peace and serenity, that view hides the seething motion of the atoms within. So understanding equilibrium is a matter of perspective, of seeing within and of seeing beyond. Because equilibrium is a state in which all temperatures are equal, it's a place where no machines operate, no geysers spray, no volcanoes erupt, no water falls. No big engines want to do any work, and no little engines can. And as long as there's fuel, coal or oil or wood or whatever works, they'll keep rolling. But if the fuel is cut off, the heat ceases to flow. The body cools, its temperature lowers little by little. And when a body finally has the same temperature as its surroundings, it's in a state of equilibrium. As long as heat flows, as long as a warm body is warmer than the cool one, entropy will increase. And it will continue to increase until nothing else can possibly happen. A state of equilibrium, and should that happen, entropy would increase no more. In other words, the state of equilibrium is the state of maximum entropy. All of nature's processes can be seen as a constant drive to increase entropy, all the time throughout the universe.
It's about a free expansion on. Okay, so in the case of free expansion, so literally you got this like oxygen tank or something, and then you just open it up while you're in space. So what's going to happen? Gas is going to escape, but it's not going to do any work on the environment because it's got gas molecules got nothing to push up against, right? All right, so now let's calculate the change in entropy of the universe from a reversible process like, I don't know, free expansion. There we go. It's an irreversible process because once the gas escapes, guys, you're not going to be able to take the gas and put it back into the oxygen canister, for example. All right, so the free expansion is the one that we usually talk about. It's very, and what we're going to be dealing with is going to be somewhat counterintuitive. Okay, so I'm using calculus symbols. This is the amount of heat that goes into the system. And if you see a slash like that, okay, so if you're going OJ on something like that, which means that it's an irreversible process. If you cut someone, obviously, you cannot uncut someone. Okay, that's a bad example. If you know who OJ is, you know what I'm talking about. All right, so if you see a slash like that, which means that this said it's an inexact differential. That's what that means. So this is the amount of heat that's going to go into the system, and it's going to increase the internal energy of the system. So this is the first law of thermodynamics. During the free expansion, there's no heat transfer. Okay, so the gas inside, boom, it's going to be gas outside. This happens fairly fast. There's no heat transfer in or out of the system. No work is being done because it's freely expanding. So there's no change in internal energy of the system, if that's the case. So the internal energy of a system can be expressed using this formula. So no change in internal energy means that there's no change in temperature under the circumstances. So, which means that, okay, so here's the change in entropy formula, a more sophisticated version of it. Number one, there's no heat flowing in and out of the system. The temperature is constant. So which means that there should be no change in entropy of the universe when there's a free expansion. But you know that's not true, right? It's not true because the gas inside the canister, when you just open up the valve, it's going to be outside. Okay, it's going to be a much more disorderly state. So which means that the fact that the gas is able to escape is going to increase the distortion of the universe. But if you're using the regular calculations from physics, it's not quite working out because it looks like the entropy of the universe is not going to change. So it cannot be because you just release the gas into different environments. You increase the entropy of the universe. Gas is in much more disorderly state. All right, so if that's the case, how do we compute the actual change in entropy of the universe? The way to do that is you have to pick a reversible process and recompute everything using a reversible process. Okay, so in this case, the reversible process that we will get to use is going to be involving the fact that the temperature is going to remain constant. Okay, so there's not going to be any change in temperature when you release the gas into the vacuum of space. So that's what we will do. So we'll pick a reversible process for this. This is the amount of work that you have to do. This work is going to be irreversible. Okay, we're going to do a reversible process. Anyway, so there's not going to be any temperature change. So this is the change in internal energy is going to be 0. So which means that the amount of change in heat is going to be the same as the amount of change in work. Okay, so any variation of heat is going to be the same as any variation of work under the circumstances. For an isothermal process, we have an expression for work. This is what we end up using. Okay, so which means that the volume is going to change at a constant temperature. Okay, so volume of gas is going to change. It's going to go from the size of the canister to whatever the size of the outside space is that it's going to occupy. All right, so this represents the amount of work done by the expanding gas into a different volume is going to be the same as the amount of change in heat that we're looking at. So now the change in heat or the transfer of heat during this process at this temperature is going to give us how much the entropy of the universe is going to change. All right, and then we end up coming with an expression. So what that means is even if during free expansion, when the volume changes, volume of that gas is changing, despite the fact that in reality there's no work being done and no energy is being transferred, entropy of the universe is still going to go up. And how much it's going to go up can be estimated using this formula. And for us to be able to make that estimation, we have to assume a reversible process. And then during that reversible process, check to see what remains constant and come up with an equation. Okay, so what I just did probably makes no sense to you guys at this point, which is perfectly fine. But hopefully this is going to make sense to you when you guys are taking a thermodynamics course at some point, because you will have to. I don't care what your major is.